welcome everybody. It's so good to see you. Good afternoon or good morning, depending on where you are coming from. I'm very excited to welcome you all to the annual webinar sponsored by the Crash Modification Factors Clearinghouse team. My name is Sarah Weissman-Pasquale, and I am the new FHWA program manager for the CMF Clearinghouse. For today's webinar, we will be talking about CMFs in real life, issues, tools, and applications. So we have, like I said, we have a great agenda for you guys today. First things first, Matt Hinshaw and I will get things started by providing an overview of the CMFs and the CMF Clearinghouse. But first, I'm going to ask Matt and each of the presenters to introduce themselves. So first, go ahead, Matt.
Yeah, thanks, Sarah. I'm Matt Hinshaw, and I'm our Data-Driven Safety Analysis Program Manager for our FHWA Office of Safety. And if you were here at this webinar last year, you'll notice that the management of the clearinghouse has transitioned from me to Sarah. And our office has seen a few position changes over the last year or so. And Sarah and I are now working close together on the programs in our roadway safety data program. I'm focusing more on data-driven safety analysis, and Sarah has taken over managing the CMF Clearinghouse in addition to her other programs. So we just want to make it clear that the baton has changed hands here. Yet we continue to work together to make the clearinghouse a strong resource. So I'll pass it to Taha.
Thanks, Matt. Hi, guys. So I'm Taha Salim here. I'm at the UNC Highway Safety Research Center, and I've been managing the day-to-day operations of the CMF Clearinghouse for about the past 4 years now. And as we go into this webinar today, I will be giving you a brief overview of the resources that are available on the clearinghouse for your assistance. And I'll pass it over to Vikash now.
Hi, everyone. I'm Vikash Gaya. I'm a professor at Penn State University. And today I'll just be talking about a couple recent projects that we did for PennDOT to estimate CMFs for high friction surface treatment and high tension cable median barriers. And with that, I'll pass it to Chris.
Hey, I'm Chris Cunningham. I'm with the Institute for Transportation Research and Education here at NC State University. I am the Associate Director for Research here at ITRI, and I'll be talking about CMFs at CFIs, continuous flow intersections. And with that, I will pass it on to who? Taha, I'm sorry.
Raghavan.
Raghavan.
Yeah. Oh, hi. I'm Raghavan Srinivasan from the UNC Highway Safety Research Center. I've been at the center for a little more than 20 years. And today I'm going to be talking about some selected CMF-related projects that have been, sponsored by NCHRP. Dr. Sarah.
Great, thank you guys. Really appreciate it. These will be some very interesting presentations on how CMFs are being practiced in the field. So we'll have some time at the end for some facilitated Q&A, and then we'll wrap up with some additional information and direction. But first, as we always have to do, a few couple of housekeeping items. First, all participants are muted due to the large number of folks that we have here today. If you have a question during the webinar, please use the Q&A button to add your question there. I know we're all very familiar with this feature. Questions that have been answered will become visible to everyone. Those that have not yet been answered will be visible only to you until it is answered. We'll do our best to answer the questions as they come in. But at the end, if we don't get to everything, we'll try to also answer some questions live during the remaining discussion time. Please note that the webinar is being recorded so that we can post it, as well as the presentation PowerPoint to the CMF Clearinghouse website following today's webinar. Finally, here's a helpful Zoom tip. If you choose the speaker view option at the top of your Zoom screen to optimize the screen, it'll make it bigger. Make it to the current speaker and have everybody at the top. That usually works for most people's settings. If you're having a technical issue during the webinar, you can send a chat to the host and we'll do our best to assist you. Okay, so first poll, we also have some questions that we'll ask sprinkled throughout the webinar today, starting with this first one to help us determine how many participants we have here today. Caroline, if you can bring up the first question, everyone please respond to this question and let us know how many people are attending from your location. As people have returned in person at their offices, we might only see one person online, but it could be a whole group of people in the office. Great, we're getting some responses. All right, looks like we're slowing down here. All right, thank you guys so much for the results. It looks like primarily we have one person logging in, but we have, wow, there's at least one group that has 6 to 10 people in one room and a few other folks that have multiple people. So welcome everybody. Thank you so much for sharing. Okay. All right. And as always, last item in the introduction, please know that our presentations here today do not necessarily reflect the views and opinions of FHWA or the USDOT, nor do they reflect the official policy of USDOT. So with that, I'm going to move on to an overview of the CMF Clearinghouse. But first, I'm going to ask Matt to chip in here.
Yeah, so we have a mixture of folks out there today on the call, and some who are just learning about crash modification factors at this time, or CMFs, maybe your first time getting exposed to this. So I just want to do a quick slide on, what is a crash modification factor? Well, in highway and traffic safety, we have studied the effects that many design, safety, and operations treatments have on how many crashes we experience after the treatment or countermeasure is implemented. A CMF is a multiplicative factor that then reflects the expected safety effectiveness of a countermeasure or treatment. And so, with this simple number, we have a data-driven value that we can do so much with. We can use data-driven safety analysis to compare the expected benefit to cost of project alternatives and, have conversations with our peers about how well countermeasures such as curve warning signage, roundabouts, rumble strips, and many others work to improve safety. So as we can see from the table, a CMF of 1.0 would indicate no changes in crashes after a countermeasure is installed. A CMF below 1 means that we expect to have a decrease in crashes. A CMF above 1 means that we expect to have an increase in crashes after the treatment or project. And we express these in terms of decimals when we're working with them analytically, typically, but we can also discuss those in terms of percent reduction or increase in crashes. So, if we're fortunate enough to have a CMF of 0, we'd expect 100% reduction in crashes. A CMF of 0.8 indicates a 20% reduction in crashes, and a CMF of 1.2 would then indicate a 20% increase in crashes. So, of course, these are pretty simple examples, and using CMFs can become very detailed, and we can even examine the effects of countermeasures on very specific crash types and severities, sort of disaggregating the results. And Taha is going to show you a little bit of how you can do that in the clearinghouse later. If you're new to using CMFs, we certainly encourage you to seek out training opportunities via the National Highway Institute and opportunities within your state that your state DOT may provide locally. Next slide, Sarah.
Thanks, Matt. All right, so what is the clearinghouse? Well, I think most of you guys are familiar with this, but just in case we have any new folks joining us here today, the CMF Clearinghouse is a central repository where we strive to store every CMF that has been developed by universities, transportation agencies, and others around the world. It is regularly updated, in fact, typically every quarter, and provides practitioners a way to search for and use the good work that you guys are all doing there to improve safety. We also have some information posted on the website for your use in working with and understanding the methodology for analyzing CMFs, as well as links to research, case studies, and trainings. Taha will show you a bit more of the website functionality shortly. Now our second poll. We're always interested to learn about how you use the CMF Clearinghouse. We have a poll to help us find out how much you use it. So if you wouldn't mind, please answer how often you use this resource in your day-to-day responsibilities. If you're attending from a group, just give us a quick estimate of the average in the room. I see Caroline's beating me to the punch. That's great. Looks like we're getting some responses in. Looking good. Ooh, we're still going. Getting almost everybody there. Looks like we have quite a few folks, a good chunk, maybe 17 or 18% that is daily or weekly, a good chunk that are monthly, and a big chunk that is once or twice per year. And never might be folks that are new to the clearinghouse, so welcome. But this is great. Thank you guys so much for sharing that. Okay. All right. So I think, Matt, you're taking this one, right?
Yeah, sure. So it's always a good reminder. People sometimes wonder how CMFs end up on the clearinghouse and the repository here. And so for a CMF to be able to be included in the clearinghouse, we established criteria in order to help us be as consistent as possible with this repository. So, here are the criteria. Effectively, a study, report, or publication needs to show where the CMF comes from, and it needs to be based on crash data. It must have had the objective of quantifying the safety effect of a roadway feature or a characteristic, and it must be focused on characteristics that are engineering in nature. And the study must have explicitly presented CMF values or functions, which is important because our team here that manages the clearinghouse, we are not deriving CMFs from the research, so they do need to be clearly presented in that published document. So if you're involved with research and CMF development, we have resources on the clearinghouse website that help give guidance on what information to include in your publication to help make sure that our team has enough information to provide proper ratings when we're adding those CMFs to the clearinghouse.
Thanks, Matt. All right, and now I'm gonna, sorry about that. We're actually not wrapping up yet. We're moving on to Taha, who will tell you more about the CMF Clearinghouse. So Taha?
Thanks, Sarah. Sarah, I think you have to stop sharing your screen so I can share my screen.
There you are, sir.
Perfect. Give me 1 second here, guys. I'm sharing my screen with you all. Perfect. There we go, guys. So as I said earlier, guys, in the next few slides, we will try to provide you with an overview of the resources that are available for your assistance on the CMF Clearinghouse. So this is the homepage of the CMF Clearinghouse. And when you go to our website, www.cmfclearinghouse.org, this is where you will come. And I think when most folks come to the clearinghouse, they come here to search for CMFs in a database. And that feature is very prominent in the middle of the screen here. However, there are lots of other great resources that are also available on the Clearinghouse website. And I just wanted to take a minute to show you where you can find some of those without getting into too much detail. So on the top of the CMF Clearinghouse page, you can see in the red box, that I've highlighted there are 4 headers about the clearinghouse, using CMFs, developing CMFs, and additional resources. We also have the feature boxes, in the middle of the website, which is a bigger red box here in the lower part of my screen. And this is where, the feature boxes are, where we used to promote the latest CMF Clearinghouse material. So for example, the feature box in the center right now is promoting this webinar that's happening today. We keep updating these feature boxes to promote the latest and greatest material that we have on our website. There's, like I said, lots of great information hidden under these headers and feature boxes. So we can go over one by one, So the first header about the clearinghouse includes a user guide along with short videos to help you navigate the clearinghouse. It also guides you on how to search for CMFs and how to filter for CMFs. There's also a FAQ tab. So if you ever have a question about anything in the clearinghouse, I encourage you to first come to these FAQs and see if it's answered there. We build these FAQs based on the questions that we get from our users. So there might be some useful information in the FAQs for you. There's also a menu option for star quality rating. This is where you will find information on how we assign the star quality ratings to the CMFs. And the second header, using CMFs, as the name implies, it includes resources to help you apply CMFs. So there's a quick reference guide there, and there's information about trainings as well as some safety analysis videos that are related specifically to the CMFs. There's also a feature that we added a couple of years ago that's called data download, or an API, if you're familiar with the terminology. So this data download feature here allows you to download the entire CMF Clearinghouse database as of the current moment. When you download the data, it gives you option to download it either into an XML, Excel, or just CSV file. This is a feature that you will use if you're trying to integrate our data into another software or tool that might be helpful to you, or even if you're just more comfortable filtering and searching through in an Excel format file. Our third option there, developing CMFs, this tab includes resources that are related to developing quality CMFs. But on this page, we also have a CMF most wanted list. And I'm not sure many folks are aware of the CMF most wanted list. So we update this list every couple of years based on things that you are searching for, but not finding in the clearinghouse, hoping that it might spur some additional research ideas. The good news is that we recently updated the CMF most wanted list as well, and Sarah will talk more about it in the wrap up, towards the end of this webinar. And lastly, under the additional resources tab, you will find information related to other CMF related topics like SPFs and benefit cost analysis. This is also where you will find state specific CMF lists. So if your state has a CMF list and we are aware of that, we put it here. If your state has a list and it's not here, but you want us to include it, you can send that list to us and we can get that uploaded here for you. So like I said, there's a lot of great information available here on the Clearinghouse. I would encourage you to take some time and explore the resources that are available to you here on our website. I also want to highlight a couple of ways, that you can search the Clearinghouse. So the first way is when you come to the home screen, there is a search bar there. You can enter any term related, any term for any treatment that you're looking for, and you can search by countermeasure name. You can also search the study abstract for that term. You can search the study citation. If you're looking for a study by a particular author, you can enter the name in the search term and select study citation, and it will bring back all the studies that are in the Clearinghouse from the specific author. Another popular way to search the Clearinghouse is using the CMF ID. So every CMF in the Clearinghouse is assigned a unique ID, and if you have that, you can enter that in the search term and just search by the CMF ID. So overall, guys, we have over 9,000 CMFs in the Clearinghouse for well over 800 countermeasures. So these are a lot of CMFs. So entering your search terms will help you narrow the amount of results that you get back. We also have a filter function on the Clearinghouse to help you further narrow the search results. So as an example here, I have included a search output for the search term roundabout. So you can see here that if I search for roundabouts, my search would result in 346 CMFs. That's much less than 9,000 CMFs that we have in the Clearinghouse database, but that's still quite a few CMFs to search through to find the one that's most applicable to your situation. To help with this, you can further filter by the countermeasure category, or on the left toolbar on the search results page is a filter option. You can filter for various things, including the star quality rating, the country, the crash type, the crash severity, whether or not the CMF was published in the first edition of the Highway Safety Manual. So all of these filter functions that we have there, they are there to help you further filter the number of CMFs based on whatever features are most important for you in finding the CMF that is most applicable to your situation. So say after you search your homepage, you filter your CMF, and then once you have applied those filters, chances are you're still going to have quite a few CMFs that meet your search criteria. Another tool that was introduced a few years ago is a comparison tool. So on that search results page, you can select up to 6 CMFs and compare them. So if you select the CMFs and compare, the results will look something like this. So in this case, it will return you the differences between each of those selected CMFs in highlighted gray and bold italics text. So for this example, I selected these 4 CMFs, and the 3 on the right are by the same author, and they apply to all crash types and all area types. But the CMFs were different. The CMFs were 0.59, 0.62, and 0.57. So I want to know, why are they different and why do they have different star ratings? So based on this comparison output, we can all see that even though they are by the same author for the same crash types for the same area type, one CMF applies to both 3-leg and 4-leg intersections. One is just for 3-leg intersections, and one is for 4-leg intersections only. So this can help us, further select the best CMFs for our application scenario. And once we find the CMF that we want, we can actually click on the CMF value itself, and it will take you to something that we call a CMF details page, which looks something like this. So in this page, it will help you better understand the CMF and the condition that it applies to. There are also some other details, like the date it was added to the Clearinghouse, and there's also a comment section at the very bottom for every CMF. So if our reviewers find something that they think would be of note to our users, they capture that there in the comments. That's a very important field. So if there's anything in there that we wanted to bring to your attention, when you're looking at CMFs, you'll find it right there. When it comes to downloading the CMFs, from the clearinghouse, you have two options. Wait, what happened here? There we go. Yeah, so you have two options. The first option is, you can use the export all search function on the search results page to download the CMFs that are relevant to your search term only. So this would only download CMFs relevant to your search term. There's also a second option that we talked earlier on about the data download API. What this does is this allows you to download the entire complete set of CMFs as of current moment. So this was last updated last month. So you'll have the latest, you can say, our whole database download in 3 formats: XML, Excel, and CSV. And there's also a data dictionary there to help you decode some of the terms that are used there. I would also like to remind everyone that back in 2021, a couple of years ago, the CMF Clearinghouse transitioned to a new rating system that was developed as part of NHRP 17-72. So this new rating system is very detailed and accounts for various factors. So we have a poll question here, for all of you, just to understand, if people are aware of our rating system changes that were put in place a couple of years ago. So there are 3 options you can choose: whether you're aware of it, you're not aware of it, or you are not sure about this system transition. I think we have some inputs coming in right now. Caroline, let us know, whenever the poll closes, that we can see the results there. Well, that's great. So we see that 38% of the people were aware of the system changes, whereas a big majority, 47%, were not aware, and 14% were not sure. Well, so for that purpose, we have this next slide here that can help you a bit more. So this is one thing I'd like to point out, in the feature boxes on our homepage, the third feature box is for the updated ratings tab. And this is where, you can find detailed information on what has changed and how it can impact your work, if you're using CMFs pre-2021 using the old star rating system. So this is all what I have for today. So these were some of the features in the clearinghouse that I wanted to highlight for all of you. Hopefully you've learned something new, remembered something that was available to you in the clearinghouse through this presentation. I want to thank you for your time. And if you have any questions for me, you can put them in the Q&A section, and we'll try to get to them at the end of today's webinar. With that, I will turn it over to Vikash for her presentation.
Thanks, Taha. I'm just loading up my presentation here.
Perfect, Vikash.
All right, I think that should be ready.
Yes, Vikash, you can see that. Yeah.
All right, thanks, Todd. Well, I really appreciate that great introduction, because I think that really sets the stage here. So now that we sort of understand from that, how to use the CMFs and what they mean, and how to find them, I'm happy to present on recent, I guess, a pair of studies that we did at PennDOT for PennDOT on high friction surface treatments and high tension cable median barriers in Pennsylvania. Before I go on, I just wanted to thank some collaborators. So this was done at Penn State. And so I wanted to thank our collaborators, Dr. Eric Donnell, a faculty member here at Penn State, Hao Liu, a postdoc at Penn State, Pengsheng Zhang, and Abhishek Prajapati, 2 graduate students that helped on these projects. And then at PennDOT, Jason Hershak and Dylan Bujek. I think Dylan's actually attending right now, so that's great. Good to see you. So the purpose of these projects, we have two separate projects, to estimate CMFs for high friction surface treatment and high tension cable median barriers in Pennsylvania. Pennsylvania, I think, had been applying these for quite some time, and realized that they believe that there was a positive safety impact, but wanted to quantify what that safety impact could be. And so we at Penn State helped to verify that through the development of CMFs for these 2 treatments. So for high friction surface treatment, we looked at the application of this treatment on horizontal roads of 2-lane undivided roadways in Pennsylvania. And we also looked at the high friction surface treatment applied to intersections. And then for the high tension cable median barriers, we looked specifically at the application on divided limited access highways. So to go into a little bit more detail, I'll start with the high friction surface treatment. So for those of you that don't know, the high friction surface treatment is the application of high friction aggregate material to the pavement surface, really to help improve the friction between the tire and the pavement when vehicles are navigating around sharp curves or particularly wet roads. So on wet, when the pavement surface gets wet or icy, if it's we kind of lose some friction there, vehicles aren't able to traverse curves or stop in time. And so the high friction surface treatment is designed to increase that friction and help with the vehicle maneuverability and decrease the stopping distance. So applied at locations where vehicles are more likely to lose control, and especially, so again, horizontal curves, or sharp horizontal curves, and especially under wet conditions. So before we began this study, we actually looked into the literature in the CMF Clearinghouse and found that there were some CMFs for this treatment. This is just a quick summary of what we found. So the CMFs ranged, you can see they're all in the less than 1 category. So suggesting a safety improvement. In some cases, a very significant safety improvement because those CMF values are very close to 0. Within Pennsylvania, so just looking across the 11 districts within Pennsylvania, there were approximately 57 miles of horizontal curves that had this high friction surface treatment. This is actually a subset of what was applied throughout the state, but this is a majority of the subset focused particularly on those 2-lane undivided roadways. So horizontal curves on 2-lane undivided roadways, and this is both in rural and urban areas. And it was fairly, the distribution was spread out fairly evenly across the state. There was one district that had no application of high friction surface treatment. But you can see here that's a total of 700 curves covering 57 miles of roadway. On the intersection side, we had many fewer intersections. Actually, I believe there are about 50 intersections total with the high friction surface treatment. But when we looked at the availability of traffic volume data, which was needed for the estimation of the CMFs, we only had about 33 intersections that we could include in our analysis. So we applied the empirical Bayes before and after method. And I know we're really focused on the results here, but I just wanted to take a quick minute to talk about this because, as Taha mentioned in the clearinghouse, the CMFs are rated. And one of the ways that they are rated is the statistical method used to estimate the CMF. And so there are various types of methods or study designs that can be used. The empirical Bayes before-after method happens to be one of the, I would say, state-of-the-art methods that accounts for many of the issues that we can see in crash data, things like regression to the mean. Regression to the mean is where locations with a lot of crashes, even if we did absolutely nothing, might randomly have fewer crashes, or tend to have fewer crashes in the future, just because it's, that could just be an outlier where, randomly we had a lot of crashes at those locations and then we're just sort of regressing to the mean value. So the empirical Bayes actually helps to account for that. It helps to account for changes in traffic volume or other design features. So it helps to control for many things that might influence our understanding of the safety performance. So this is actually a 3-step process. I'm not going to go through the steps in a great amount of detail, but in the first step, we actually develop a safety performance function, which is basically a statistical model to predict how many crashes would occur at a location if we did not have the treatment. So in this case, PennDOT put down high friction surface treatment at these intersections and these curves, but we need to kind of ask ourselves a what if question. Well, what if they did not do that? What if they did not put that high friction surface treatment? There's no way to know what would have happened if that treatment was not installed. And so we have to use a statistical model to predict what we would have expected if we did not put down that treatment. So that's the second step, is we use that model to predict what would have happened at the treatment locations if the treatment had not been applied. And then the last step is really compare what we predict would have happened and what we saw or observed, or in terms of reported crash data, what actually happened at those locations. So it's a 3-step process. And so in our work, we actually had data from tens of thousands of horizontal curves across the state in both urban and rural areas and on all of these 2-lane undivided roads. And so we developed statistical models in that step 1 to predict what the safety performance at these individual locations would be at the locations without the high friction surface treatment. And so in doing that, we accounted for various different roadway features or the presence of different safety influencing features. So we accounted for traffic volume, curve length, the degree of horizontal curvature, so essentially the radius of the curve, but the inverse of that, the number of adjacent horizontal curves. So if there was a horizontal curve that occurred on the roadway sort of in isolation with long tangents upstream and downstream, or if there were adjacent curves upstream and downstream that might influence the driver's perception of the curve. The speed limit on the road, we also accounted for the year because we had a very long study period. Our crash data was from, I want to say 2007 to 2021. So a very long period. So we wanted to account for temporal changes that might have occurred. We accounted for spatial issues across the state of Pennsylvania. So there's 11 engineering districts. So we accounted for changes across those engineering districts. And then lastly, which I think was a little bit unique, we accounted for the presence of horizontal curve warning signs. So some examples are shown here, and how if the presence of these curves would sort of affect what we would expect in terms of safety performance at a subject curve. With that, I can actually just jump straight to the results. We took that information, predicted at our horizontal curve locations with the high friction surface treatment, how many crashes we would have expected, and then compared the number of crashes that we observed to get our CMFs. And so we did this for a large number of crash types. And this is a very, there's a lot of text here, I understand. The crash types are on the left. And the numbers that are kind of highlighted there in green represent our CMF values. And so the CMF values are all less than 1, which suggests that the high friction surface treatment is associated with a decrease in crash frequency. That the CMFs range from about 0.3 to about 0.67. So 0.3 would be associated with a 70% reduction in that particular crash type. 0.67 would be associated with a 33% reduction in that crash type. So somewhere between 33 and 70% reduction in the individual crash types. And the crash types that we considered total crash frequency, so all crashes, fatal and injury crash frequency, property damage only, runoff of the road, wet road crashes, head-on crashes, sideswipe crashes, and then within those individual categories, run off the road, fatal and injury crashes, hit fixed object, fatal injury crashes. I think I missed that one from before. Hit fixed object is HFO. Wet road fatal and injury crashes, head-on fatal injury crashes, and then sideswipe fatal and injury crashes. We also looked at the statistical significance of these CMF values. Essentially, if these CMFs are statistically different from the number 1, which represents no change associated with the installation of the treatment. And all of these were statistically significant at the 95% confidence interval. I think, I can't speak for any agency, but as a researcher, I remember meeting with PennDOT and saying, the CMFs are so good, apply this everywhere, right? This treatment is just these large reductions in crash types that we care about. If it's a low-cost countermeasure, this seems very, very effective. We also broke those up just on curves on urban roadways and curves on rural roadways. The numbers change a little bit, but the story is essentially the same. The CMFs are all statistically significant, meaning they're different from 1, and they're all less than 1. So statistically less than 1. So they're all all changes were associated with a reduction. A reduction in crash frequency and a significant reduction in crash frequency. At the intersection level, we had these 33 intersections of these different types. So there were actually 33 intersections of these different intersection types. So 3-leg minor stop controlled on urban suburban collectors, 3-leg all-way stop controlled, so on and so forth. So we actually used SPFs from existing PennDOT projects that we had actually developed as a part of previous projects. And when we looked at the application of high friction surface treatment at the individual intersections, again, we found, we estimated 2 CMFs, 1 for total crashes and 1 for fatal and injury crashes. Both CMFs were highly statistically significant and much, much less than 1, indicating a reduction in crash frequency, a significant reduction in crash frequency. So in total crashes, a reduction of about 66%. And then in fatal and injury crashes, the reduction about 75%. So high friction surface treatment seems to be a very highly effective countermeasure at horizontal curves on 2-lane undivided rural roads, as well as intersections. Moving on, talk about the second project, high tension cable median barriers. So high tension, median barriers are designed to prevent cross-median crashes. So on a limited access facility, a vehicle sort of leaving the roadway on the left, crossing the median and striking vehicles that are traveling the opposite direction. These cross-median crashes tend to be highly, result in the more severe injury outcomes. Vehicles are traveling at high speeds. Vehicles in the opposite direction are traveling at high speeds. That usually leads to a large amount of kinetic energy and catastrophic outcomes. So high tension cable median barriers are placed down in the center of the median to sort of serve as an object for the vehicle to hit before it crosses into the opposing traffic. And the high tension cable median barriers are sort of a lower cost median barrier that consists of tension steel cables onto posts that really hopefully prevents the vehicle from entering that opposite traffic lane. So the benefits, it's more cost effective than the median barriers, the traditional median barriers. Actually has minimal disruption to sight lines. You can essentially see right through them, unlike the traditional larger barriers. And the hope is that it will contain the vehicles again before they enter the opposing traffic lane. So we looked again at the literature before we did our study. The literature suggests high tension cable median barriers reduces frequency of severe crashes, which is what we would expect. But it actually increases the frequency of the least severe crashes, which actually makes a lot of sense because vehicles that would have entered the median and maybe been able to recover and enter back onto the road, their travel lane without a problem, now there's an object for them to strike. And so, it's increasing the total number of crashes, but increasing the number of crashes at the lower severity levels, maybe property damage only. So you can see here that in Michigan, there was a study that found, PDO and possible injury crashes, a CMF of 2.5 to 2.7. That's an increase in the number of crashes by, 150%, which is a very significant increase. So within Pennsylvania, there were approximately 750, maybe 760 miles of high tension cable median barriers that were installed. 900 miles of cable median barrier installed within Pennsylvania. We were using the PennDOT defined roadway segments for our analysis. So when we kind of mapped those installations onto a segment that had the high tension cable median barrier installed onto the entire segment, that was 760 miles. So that was actually our sample size. The other 180 miles, that was where the high tension median barrier was installed on a portion of a roadway segment. And we wanted to exclude those because we were using the PennDOT defined roadway segments in our analysis, and we couldn't tell, if a crash happened there, was the high tension cable median barrier responsible? Could it have made a difference? It was very difficult to tell. And since we had such a large sample size of 700 miles plus, we felt like it was okay to sort of eliminate those partial installations. We also had different types of high tension cable median barrier installations. So there was those that were installed on one side of the shoulder, those that was installed in the median, so the center of the median, so one installation in the center designed to cover both sides, and then those that were installed on both sides, so on the shoulder, but on the two installations on the median, one on each shoulder, essentially, two opposite directions. So we actually disaggregated our CMFs based on these installation types. I actually don't show it in the presentation just for time purposes, but if anyone's interested, we can talk about that as well. So when we developed our SPFs for the divided freeways, we considered the following explanatory variables. We considered traffic volume, segment length, the degree of curvature per mile within that segment. So how basically the curviness of the roadway segment, the presence of inside and outside shoulder rumble strips, the presence of on and off ramps, the presence of an outside barrier, the posted speed limit, and then indicator variables for year. Again, the temporal, again, we were using a very large time horizon for analysis, I think 2007 to 2021. And then an indicator for the PennDOT engineering district, just to look at the spatial differences across the state. Our results were actually in line with what we saw in the literature. So the CMFs that are highlighted in red there are all greater than 1, indicating an increase in crash frequency associated with the high tension cable median barriers. And the CMFs that are in green are less than 1, associated with a decrease in crash frequency. So what we found is that the high tension cable median barriers was associated with a 13% increase in the total number of crashes on these segments, which sort of makes sense because, again, there's something on the road that's there to hit that otherwise wouldn't be there if there was not a median barrier. At the fatal and injury level, there was actually a 3% increase in the number of crashes, but this was not statistically significant. So essentially, it's statistically equivalent to 1. So statistically no change in fatal and injury crashes. Property damage only crashes increased by about 20%, and that was statistically significant. We then broke it up a little bit more. So hit barrier crashes, so crashes that involved a hit barrier. When you add a barrier, it increases by 180%. So that makes sense. I add a barrier, hit barrier crashes increase. The hit barrier crashes can also include the outside barrier as well. So that's probably why there were some hit barrier crashes at these locations before. Cross median crashes reduced by 80%. KA crashes, so crashes of the highest injury severity levels, fatal and suspected serious injury, is 0.65. So that's a reduction of about 35%. And then lastly, KA cross median crashes, the CMF was 0.1, which is associated a 90% decrease in cross median crashes, KA cross median crashes. And then lastly, we disaggregated the CMFs based on urban and rural sections. I forgot to mention it before, but one of the things we looked at in the literature is actually there's a lot of, the previous studies that were done on high tension cable median barriers focused on rural areas. And so this was a unique case where we actually had urban and rural areas. So we disaggregated our CMFs by rural applications and urban applications. In general, the story is the exact same. In rural or urban areas, it's an increase in total crashes, a net neutral in the fatal and injury crashes, an increase in property damage only crashes, and a large increase in hit barrier crashes. However, we decreased the crashes of the highest injury severity levels and the crashes that we are actually trying to particularly fix. So the cross median crashes decreased significantly. The number of KA crashes, so the fatal crashes and the highest injury severity levels decreased significantly, and then the KA cross median crashes are almost eliminated. So with that, I saw that there were some questions in the chat. I will go through and answer them. I can type them out just in the interest of time. I also saw that there was a hand raised or something like that. I guess maybe we'll have some questions at the end. But if that's it, maybe I'll just move on to the next presenter. So thank you very much for your time, and then I will pass it over to Chris.
Thanks, Bakash.
Thanks, Bakash. Let me share my screen real quick. All right, so thanks everybody for coming. I appreciate Bakash's presentation. That was very interesting. Today I'm presenting on a topic, a research project that NCDOT funded us for. They, like a lot of states, are interested in alternative intersection designs. North Carolina is particularly interested in alternative intersection designs. And one of the ones that we have not seen installed in North Carolina at the time of the funding of this project was a CFI. And so a CFI, I'll explain that in a minute, is a continuous flow intersection. And we'll talk a little bit about some of what the literature shows and why there was some confusion. I want to also recognize a few of my other authors who are on this call today, so they can answer your Q&A while I'm talking probably and save me that burden, hint, hint. But Taha, Salim, and Srini. And so I appreciate both of them. And then Taehan Lee is now at the Korean Expressway. So just a quick outline. I'm not going to go over that, but these are the items that we'll cover today. So just to make sure everybody's on the same page, I take for granted that everybody understands how different alternative intersections work, and I've learned that that's not always safe. So a CFI, if we have a main intersection that would typically be at the blue box here, that's signal controlled, and we want to make that more efficient, which is typically what a continuous flow intersection is put in for. you can take the left turns and pull them upstream of the intersection and then divert that as a leftover. And that makes it more efficient because now the left turn can go with the what was conflicting through movement without a conflict. And so that makes it more efficient. So what we're particularly interested in is what happens when we divert this left turn upstream and make a signalized crossover here. How does that affect the overall intersection safety? So the objective was to investigate the safety impacts of conversion from a conventional signalized intersection to a CFI. And this was a national study. So this was nationally focused, looking at this treatment in several states. So there was a few questions that the panel was specifically interested in. Some of you might be interested in that also, is what is the anticipated overall safety impact? So just overall, and we saw some basic findings in the literature that conflicted with each other, and I'll talk about that in a second. But they were also wanting to know, are there any specific geometric features that they could focus on that might improve the safety if they consider that alternative design scenarios? There's something different about CFIs that might be less or more safe. And then they wanted to look specifically at the crash types, which is very typical in these types of studies, and also the crash severity. So really high level, if you're trying to look at the safety of alternative intersections, you'll often look to conflict diagrams. And so a typical conventional intersection, you'll have 30 to 32, depending on type, 32 typically. Conflicts with 16 angles, 8 merge and 8 diverge conflicts. And so we're trying to reduce these types of conflicts. And so if we go to a 4-leg partial CFI, where basically the diverging left turn upstream is on 2 of the legs, that's pretty typical, you'll decrease the number of conflict points from 32 to 30. And then if we go to a full CFI where the diverging lefts happen on all the approaches, you'll go from 32 to 28 conflict points. And so you've reduced mainly the angle type crashes or the angle conflicts, crossing conflicts. And so in theory, it should be safer not having looked at crashes. However, when we looked at some of the previous work, and this is where NCDOT was really conflicted, one of several reasons why they were really conflicted on installing CFIs as a treatment, and they looked at studies, they saw different study methods. So they saw comparison group methods primarily. And when they looked at the CMFs, they conflicted. And so we had a CMF which showed a 24% increase in crashes. And then when we looked at another study in Utah, what showed a 13% decrease in crashes. And then a 2020 study showed an increase of 11% in crashes. So there's a little bit of variation here, and there was some uncertainty with the method of study that was being done also. So they wanted a more comprehensive study. So we started by looking at where CFIs were located, and we have a database here at the university that we put together a long time ago, looking at alternative intersections. If you're interested in that, let me know. I can send you the link to that. It's not been updated, honestly, in a couple of years, but it's very comprehensive up to that point. We had 45 possible CFIs across 13 states. And in North Carolina, at the time the study was actually funded, had just put in their first CFI, so we weren't really able to do much with that. So you can kind of get a sense of the breadth of what we were looking at as our starting point. And what North Carolina DOT was hoping for is that we'd be able to get data on at least 20 of those sites. That's what we were shooting for. So obviously, if you've ever done this type of research, you know getting the data is the hardest part. So of those 45 sites, 27 were a typical CFI. One was a full, so it had 4 approaches that had the diverging left upstream, and 26 were partial CFIs. And then there were several non-typical CFIs. For instance, you might have some grade separation at an interchange, or it might be a very unconventional design. It would not be the standard design. So we really didn't want to muddy the waters. So we kind of had a starting point of 27 actual CFIs that we thought we might be able to capture some data from. And so when we break that up by the number of legs that were actually diverging, we had 48 possible legs at those 27 typical CFIs. 3 of the intersections that had 3 total legs, there was 8 or excuse me, there was 8 legs, and then at the intersections with 4 total legs, there was 19. And you can see how those break up. So obviously we wanted to have reference or comparison sites depending on the study method that we were looking at. So we had some criteria that we set with the panel. Our team set with the panel first that we obviously wanted it to be located in the same region for seasonality primarily when we have rain or snow events or something like that. We wanted standard 3-leg or 4-leg signalized intersections with 2-way approaches, so no one-way approach movements. We wanted them to be similar sites as possible conversions at some point. We wanted no major geometric changes, obviously, from the before to the after period that would impact how the reference site would change over time. And then we wanted at least, and I'll explain this in a second, but we wanted at least 150 feet away from any component of the intersection. So 150 feet upstream and downstream of the stop bars, you can think of it like that. And then we obviously needed volume data. So they should be able to at least give us some AEDT data or some kind of turning movement count data over time. So when we looked at the sites and we had 27 typical, only 19 were possible based on the state's willingness to give us data. And so we went from 27 to 19 just based on email conversation and phone conversation with various state DOT safety units that were willing to give us data. So we started with 19. So we labeled them T1 to T19. You can see the states that we were looking at once we got to that point. And then as we started getting data and looking at some of the more detailed nuances of the sites, we had to remove 3 more. And so the 3 that we removed was T5 in Baton Rouge, Louisiana. We realized it actually had an unusual design. And if I recall, that was the one that had driveways on the divergent left, where driveways could right in, right out, or maybe even left in, left out, if I recall, depending on the site. But anyways, it was very unusual that driveways accessed that divergent left. And then T6 in Maryland, we deleted because we weren't able to get any AEDT data on that site, which we needed for EV. And then T17 in Utah, their database, it was an older site and their database did not have the amount of before data that we needed, and there was a database change. So we just decided to eliminate that site also. So we looked at 16 typical CFI sites that we were able to capture data from. And so you can still see most of those were 4-leg sites. We had a couple 3-leg approaches, and then we had some diversity in rural, suburban, and urban sites also. So one important thing to note that you probably wouldn't think of, you might have asked somebody on this call or on this Zoom meeting might have asked themselves, well, the 150 foot, how did you apply that to the CFI? Because that's not a standard intersection. You actually have a main intersection. And if you have a partial CFI like this one, where you have divergent lefts on the eastbound and westbound side, where does your 150 foot measure from? And so we had a lot of discussion internally in our team about this because 150 foot from the main intersection would only include, this space, if y'all can see my mouse, but it would not include the space up to the next stop bar at the divergent left. So how should we treat that? Because it's going to be really hard to clean that data unless we get like really detailed crash diagrams and crash data. And a lot of states were not willing to give us the crash diagram in the narrative. And so we said, let's be conservative about this. Let's just take the outer stop bars, whatever the outermost stop bar is for that entire intersection. We're going to go 150 feet back from that. And then we're going to allow the crashes that stay in this little segment where this stop bar would come back to 150 feet. We're going to let them just stay in our prediction here. And so in that way, we won't overestimate the safety effect. If anything, we'll underestimate. We'll be conservative. And so we're basically saying the numbers that you're getting ready to see are conservative estimates for that reason. So we gave results for 3 different methods. We used the comparison group method. It does not account for regression to the mean, but some would argue that the comparison group method, for those that kind of understand safety studies, that would be sufficient because most CFIs are not put in for safety, they're put in for operation. And so because of that, you would expect to see no regression to the mean is what some would argue. However, we had a lot of debate about this in our meetings, internally and externally too, because regression to the mean could still be possible if we put this treatment in place and now more vehicles come to that site because it's more efficient. And so we really thought that it made a whole lot more sense instead of just doing CG to look at empirical bays also. And so you might be able to, as we go through this, you might on the side just want to compare the comparison group to the EB results and kind of see what those show. They weren't really that different, but there's a possibility that more vehicles might want to come to that site because it's more efficient. And we also provided the naive results, which is just basic before and after for reference. So you can see that. Oops, sorry. All right, so you're going to see several crash categories. I just want to introduce those before we look at the tables. We're going to look at aggregate versus disaggregate. And what I'm basically saying here is look at total crashes versus some of these disaggregated crashes that we want to look at, like area type. Is it rural or urban suburban, for instance? The number of approaches. Is it a 3-leg or is it 2 approaches, 3 approaches, 4? Like those kind of things is what we're looking for. Or the number of crossover lanes. Is it crossing over with, on this, for instance, is it crossing over with 2 lanes or 1 lane? Is the intersection on a skew? That might play into it in some way. And then, of course, one that you should be particularly familiar with, because we're going to reference it a couple of times here, is the right turn treatment. So I'm going to just pause for a minute to explain that. So the right turn of a typical CFI would be this, what I'm going to call the parallel right turn. This would be the one that you would typically install if you did not have a right-of-way issue. And so in this case, what would happen is the divergent left turn, or the left turn that crosses over, would be running parallel to the main line, and then left coming onto the side street. And then the right turn would come parallel to that on the outside and then merge downstream. The standard right turn, so if you think of like a standard right turn at a standard intersection, the right turn happens at the main intersection. And so if you didn't have enough right of way to slide that parallel right turn and then come up here, you might just say go to the standard location. And so in some right of way constrained locations, we saw this type of design. And so that is something we wanted to look at. So just kind of keep that in mind. We're going to look at the parallel and the standard here, the parallel being the typical. And then the crash category, similar to Vikash, we wanted to look at crash severity, and we put fatal and injury, KABC, all together, and then PDO we broke out. And then we looked at different severities. So we had total crashes, then angle and rear end. We broke out separately to look at those. So first and foremost, we looked at the aggregated crashes. What would be the CMF overall if we looked at these 16 sites? And so what you can see here, and the one, if you want to do some comparison, you can, but the one really to look at is the EB. And so this would be the primary one, would be the primary column that we'd be looking at here. So for total crashes, looking at these 16 sites with everything aggregated together, we'd expect a 12.1% decrease in crashes. And then you can look at the next 2 rows here. If we look at injury, fatal and injury together versus PDO, both of those reduced significantly at 95%. And then if we look at crash type, which the 2 main that we focused on were angle and rear end, we looking at about 30 and 13% reductions in angle and rear end respectively. So all positive results. And so overall CMF, that looks really, really positive. So then we looked at the area type. And so one thing to keep in mind here when you look at these results is that the rural sites of the 16, only 2 of those were categorized as rural. And so you can kind of take the findings for this a little bit with a grain of salt, but it's still, we gave the results for it and showed whether it was significant. And then the suburban sites and the urban sites we lumped together, and there was 14 of those. And so the key finding here is that when we look at the same total and then the 2 injury crashes together versus the angled rear end, we saw statistically significant results that were on the order of 40% or even 54%. So 54% to 30%. And again, it's a low sample size, but rural sites seem to be very promising based on that very limited sample size. And then when we looked at urban and suburban, we didn't see as consistent results, but we did have a higher sample size. So at urban and suburban, we saw about a 7.3% reduction, and that was significant at 95%. And then when we looked at the injury, both of those were significant at the 85 and 95% level. And then when we looked at the crash type, angle crashes reduced significantly by about 30%, but we did not see a significant change in rear end crashes at the urban and suburban sites. So all of those would be positive results or null in certain cases like rear end crashes. So that's still a good treatment impact. So then we looked at the number of approaches. And so we had 3-leg CFIs and 4-leg CFIs. And so this would be like the T intersection as an example versus the 4-leg intersection. And so basically what we saw here is that the 4-leg sites, and again, sample size, just keep this in mind, was 3 and 13. So that does matter. And so what we found here was that for the 3-leg T intersection sites, overall, we saw a 14% decrease. We didn't see any increases that were significant in any way, but we did see a decrease in rear end crashes at the 3-leg sites. So overall, you would say that was still positive if you were looking at a T intersection for a CFI. But the 4-leg sites were significant at the 95% level all the way across the board, especially angle crashes. We saw a 31% decrease in angle crashes and a total CMF of 12%. So all very positive at 4-leg CFI sites, which is typically where you would install these. Then we looked at the number of crossover lanes. So this is the diverging left turn where it crosses over the through. So in some cases we had 1 left turn lane, and in some places we had 2 left turn lanes. And to be honest, this one is one of the ones that kind of surprised us, but we think it kind of makes sense and can be explained. So we have fairly equal sample sizes across the board here. Not exactly, but we did have a little bit better representation of sample sizes from 1 to 2 than we did in the prior 2. But what we saw here is that single lane crossover sites had less significant safety impacts than 2-lane crossover sites. And overall, we didn't see a safety impact for single lane crossover sites, but we did see that it increased PDO severity crashes, and it increased rear end crashes. And so that kind of raised our eyebrow a little bit, especially when we looked at the number of crossover lanes being 2, where we saw significant results across the board. And we kind of asked ourselves, why might that be possible? And so what we think is happening is that obviously 2 crossover lanes is going to be more efficient than 1 crossover lane. And we think what's happening is because those 2 crossover lanes are being put in place, is there's less aggressive driving maneuvers, especially those people in the back of a queue trying to get through that left turn. So we think with those 2-lane crossovers are helping reduce that aggressive driving behavior that might be present at the single lane sites. And so we would recommend, if it's possible, even if it's not necessary at that time, it might be good from a right-of-way standpoint to plan for 2 lanes at your crossovers for any future traffic, just to make sure you reduce that potential for aggressive driving behavior. So then we also looked at intersection skew along with the right turn. And so if we looked at the sites that there was 13 sites that there was no skew present, and there was 3 sites that there was skew present. And so I believe, if I'm correct me if I'm wrong, Srini and Taha, I should have looked this up beforehand, but I believe we considered an intersection to have skew when we crossed 70% or 70 degrees based on the Green Book. And so anything that was greater than 70 degrees, 70 to 110 degrees, we consider that not to have any skew, that was within design guidelines from the Green Book standpoint. So of the 13 that had no skew, the parallel right turn, so this is the parallel as a reminder, this is the typical design. We had 8 in our sample size, and we saw that there were reductions across the board that were significant, 95% confidence level. So a 30% overall, or 29.3% reduction in crashes overall. And then we saw reductions, especially of angle, of 52 to 53% reduction in crashes at those no skew sites with the parallel. But interestingly, when we looked at, again, no skew, but when we looked at the standard right turn, where the right turn would come up at the standard location because you don't have enough right of way maybe to put it in, we did not see the same results. We saw a significant increase in overall crashes of about 16%, and then PDO crashes increased by 21%, and rear end crashes increased also by about 23%. And so what we believe is happening here is that this right turn, the stop bar right here, is really a long ways away from the through movement that's conflicting on the other side. And so when vehicles are looking over their left shoulder, trying to look for a gap, maybe to turn right on red, that there's a safety impact that is showing up here for that right turn at the standard location. So obviously we would recommend the parallel right turn over the standard. And that if you're going to consider a standard for right-of-way reasons, you really need to look at that closely, maybe even not allow right turn on red, something like that, because you're going to potentially have a safety problem that you're not particularly prepared to address. So then we looked at the skew present. This was 3 sites. We did not have any standard right turns. That's the top drawing here. Where there was skew present, we only had skew present with a parallel right turn, which is the optimal design based on what we saw earlier. And when we look at this one, it looks like when there's skew present, if you put in the parallel right turn, it actually is safe. And so the CFI can be used at a skewed intersection based on what we're seeing here with a parallel right turn. So you're removing this right turn conflict that's happening at the standard intersection. You're letting it merge downstream. That seems to help safety. We did not see anything increase significantly. It does show an increase in angle, but it was not shown to be significant. So it was not different than 1, is what that's saying. So just overall conclusions, just looking at the total crashes from the aggregate data, we can say that there's a CMF or a 12% decrease, and it was significant within 95% confidence, and that all crash types and severity reduced significantly. And then when we look at the categorical data or the disaggregate data, rural sites were much safer than urban sites. I know you don't really get a say in that when you're considering a CFI, but you can just know that a rural site is going to perform a little better from a safety standpoint. And that 4 approach sites were safer than 3 approach. Now, the numbers don't show that here, but when you look at the severity and the crash types, it supports the 4 approach site being more safe overall than the 3 approach T intersection site. So they can be used at both, but it's actually a little safer at the 4 approach. 2 crossover lanes was much safer than 1 crossover lane. And then, so we would recommend, if at all possible, always installing 2 crossover lanes, even if it's not necessary for the volume that's there today. Go ahead and take advantage of your right of way. And that parallel right turns were much safer than standard right turns. So pretty much in every case, the parallel is going to be a better design choice. And if you have to use the standard, you really need to consider that carefully. If you're right of way constrained or something to that effect, and think about how you might draw down on those crashes for that right turn movement. And then skewed intersections with parallel right turns seem to be just fine. We didn't see any problems with that. So the CFI works at skewed intersections, at least with the parallel right turns. So just some future research considerations that we thought about as a team. There are still several states that did not respond to our request for data. There were 24 possible sites. We obviously removed 3 of them for various reasons where we couldn't get data. So there's 24 possible sites. We only got data from 16 of those. And then if we had the narratives and the crash diagrams, we could clean that data a lot better. And there's a lot of other potential research areas that we could look at if we had those narratives and crash diagrams. So if you're one of those states that is really hard to get narratives and crash diagrams from, it sure would be nice as a researcher coming from outside of the state to be able to access those in some way and still protect the identity of the people that are on those crash reports. So most states we have found don't provide that level of detail. And with that, I'm done. I'm going to hand it off to, is it Srini?
Yes, Chris, I'll be training now.
Yep. All right. So are you able to see my screen?
Training.
Yes.
Okay. All right. So I'm going to be giving a brief presentation on some selected current recently completed CMF-related NCHRP projects. Yeah, so I'm going to talk about these 5 projects. One of them, 7660, was completed a few years ago, but the NCHRP decided to publish them last year. The 1772, 1795, they were completed within the last 1 year. 17104, 108 are ongoing projects. Okay, 1763, this project developed many procedures that can be used by practitioners, and some examples here in the slide. Now, the Appendix A from this research provides a step-by-step procedure for estimating the safety effect of a proposed treatment for a particular subject site. So this includes determining the characteristics of the site, identifying existing CMFs, and in some cases, maybe developing an overall CMF for the subject site. And Appendix B provides a procedure for combining the safety effect of two treatments. There are multiple methods that were developed as part of NCHRP 1763, and this procedure kind of talks about which method will be more or less appropriate for a particular condition. And Appendix C from this project provides guidance for developing crash modification functions. And then we also have in this project some software that were developed primarily using Microsoft Excel for implementing the different methods that were developed as part of 1763. As I said, this project was completed many years ago, but for some time, NCFHS did not make a decision on whether to publish the results. And last year, they decided to publish the results. So the final report came out as NCHRP reports 991. And then there are also videos that are explaining some of the procedures that are developed in 1763. And these videos were developed with support from Federal Highway, and these can be accessed in the links that are provided here. Okay. Now to a poll question. How does the agency estimate the combined safety effect of two treatments? And you can select all that apply. Okay. See the results coming up here. Okay, so it looks like engineering judgment is used about half the time, and the quantitative procedures such as in 1763 or other sources close to about 50% of the time, and then other sources about 27% of the time. Thank you, Caroline. Okay, now on to NCHRP 1772. This was a pretty large effort that spanned multiple years. And there were some original objectives that were prescribed in the beginning of the project, but a few things were added as the project went along. Initially, the objective was to assess the existing process for identifying CMFs for inclusion in the second edition of the HSM, and then develop proposed revisions to the criteria and process, and then apply the any new method that may be developed to develop a list of CMFs for the second edition. And then some other things are added, like, for example, conducting a CMF gap analysis to identify topic areas for which more research may be needed, developing a guidance document for practitioner use, conducting something called a single-state calibration, which is essentially calibrating the safety performance functions before they're included in the second edition, and then develop CMFs for roadside crashes. Okay. So in terms of one of the first objectives was to develop a new rating system for CMFs. So we reviewed the rating procedures developed by others, including the CMF Clearinghouse rating system that was developed in 2009. But there are also other rating systems that are used in the US as well as in Europe. And then after looking at these, we developed a more detailed procedure for rating CMFs. And the current CMF Clearinghouse rating system is actually based on this process. And I think Taha kind of mentioned this in the beginning of this webinar, that we have a new system that was incorporated about a couple of years ago. And so this actually was based on the 1772 system, more detailed than the previous system that was developed in 2009. Okay. In addition, in the 1772 project, we also developed a guidance document, which potentially could be used in Part D of HSM2. But this includes all these topic areas, introduction, a chapter on selecting CMFs, how CMFs could be selected when you have multiple CMFs available for the same countermeasure based on multiple studies, how the CMFs could be applied, developing CMF, which is mainly for researchers, who have knowledge of current techniques, and then Appendix A was the summary of the 1772 rating system. Appendix B was looking at, how to adjust CMF for local conditions. And then Appendix C was combining multiple CMF for the same countermeasure. Again, that Appendix C actually is based on the 1763 project that I mentioned earlier. Now, this document was developed as part of 1772, but eventually the decision about how it's going to be used will be made by this HSM2 production contractor, who is actually, that's which work is actually being led by Texas A&M University. Okay. The other one was topic area that was covered was something called the single state or common state calibration of HSM2. And this, by the way, for some of you who are familiar intimately with the first edition of the Highway Safety Manual, this single state calibration was also done before the SPFs were included in the first edition. And the goal here is because the SPFs from the different chapters were developed by using data from different states, by doing this common state calibration, you facilitate the comparison of the predictions without calibration. And so in 1772, the rural segment SPFs were calibrated data from Ohio, the urban segment SPFs were calibrated data from North Carolina, and the intersection SPFs were calibrated North Carolina data. So one challenge we had here was there are a lot more prediction models, a lot more facility types in the second edition compared to HSM1, so that there were some limitations in what we did in terms of the sample size. Again, this production contractor is considering on how these factors could be used in the next edition of the upcoming second edition of the Highway Safety Manual. The next topic is on the CMF roadside characteristics. As many of you may know, in the first edition, the roadside hazard rating is 1 through 7. And essentially, there are photographs of different conditions. And it's somewhat of a, when you're trying to use photographs, somewhat of a subject procedure. And there was some discussion about trying to do a more objective system. And NCHRP 1754 actually did that. But there were a lot of inconsistencies in the procedure that were found by the HSM ASTO committee. So 1770 was asked to develop something, kind of build on 1754 and previous research. So we actually did that. But I'm going to be mentioning that 17104 is another ongoing project. Will build on this again to develop something more robust than what was developed in 1772. The last topic that was covered in the 1772 project was the gap analysis. So looking at the overall quality of CMFs in different categories, and then figuring out the gaps and providing insight of future research areas. And then the 1772 report has been published as NCHRP report 1029. And there's also a supporting web-only document, which includes the appendices to the report, and also some other supporting documents providing the list of CMFs with the 1772 rating system, and also the old rating as well as the new rating for all the CMFs that were converted with the new rating system. Okay, now to 1795. This project, the goal originally was to develop CMS for commonly deployed ITS applications, and then provide case studies of safety, benefit, or cost ratios for such ITS applications. I initially considered all of these treatments. So the variable, dynamic message signs, CCTVs, traffic monitoring stations, ramp meters, and road weather information systems. But in this project, so we were able to complete phase 1, which was a literature review and data assessment. And then we developed a work plan for phase 2 that was approved by the panel. And then we had selected Utah, Pennsylvania, Arizona to be the states that would provide us with the data. But there were significant delays in obtaining the data. So we had to, NCHRP had to make a decision on, how to proceed further in the project. So essentially, they made a decision for us to complete the project with data from Pennsylvania alone. So essentially what we did was we developed a procedure, that a procedure can be used with practitioners for estimating changes in crash frequency for specific application circumstances, specifically for CCTV, dynamic message signs, and RWS. And this was essentially just data from Pennsylvania. And we provided, a kind of a document to NCHRP for them to consider for publication. But the results from this will be presented at the 2024 TRB annual meeting in January. Now 17104 project. This project essentially, the goal was to validate roadside SPFs and CMS that were developed in 1754, but also based on this review, develop possibly some new roadside SPFs to supplement existing models. And this essentially would build on the work that was done in 1772. Also, eventually coordinate the research projects with the manuals such as the Green Book and the Roadside Design Guide. So essentially, phase one of the project has been completed, and essentially we are waiting for funding to come so that we can do phase two. So essentially, we have done the literature review, we assessed the data, we've developed priorities to focus on rural two-lane and rural multi-lane non-freeway roads. And we're going to be using data from Minnesota, Kansas, and Washington. And then at the moment, we've kind of developed a plan for how to sample the roads for data collection, because the resources are limited, but this is a pretty extensive data collection effort. So it has to be a careful sampling approach so we can maximize the chances of obtaining the necessary data. Okay. All right. 17108 is the last project I'm going to talk about. This is actually, the goal is to develop CMF for alternative intersections, is being led by Taha, my colleague. So the goal here is to determine the current knowledge research gaps in quantitative crash prediction methodologies for alternative intersections, and then develop, validate, and statistically validate crash prediction methodologies to quantify the safety effect of these intersection types. So essentially, we have completed phase one, completed literature review, conducted the practitioner survey to determine which type of intersections would be higher priority, identify the states for data collection, identified, assess the readily available data, and then we have, these are your prioritized list. And of course, this could change depending on, as we proceed with the data collection, the ARCET intersections, the continuous flow intersections, the diverging diamond interchanges, the continuous green T, and the median U-turn. And I would likely, depending on the data, probably focus on the first three, which was a higher priority for the panel. But again, that might change depending on our data availability. Okay, the next steps, essentially, we have submitted a revised phase one report, which is currently being reviewed by the panel. And if that report is approved, then we go into data collection, and then data analysis, and then developing the CMFs for practitioner use. Thank you.
Well, I want to thank everybody for all the great questions that we saw. At last I checked just a second ago, I think we have answered everything. However, if there are any other questions that you guys have, you can upload them now. We just have a couple minutes to answer them. Otherwise, a big thank you to everyone for their guest presentations today. You guys did a great job. I just have a couple of things before we wrap up. One item that we are actively promoting is to cite the site. If you have a question about where to find the CMF ID, it's really important that when you do research, when you do your own studies or reports, that you identify which specific CMF. As you know, Taha was mentioning, we're well over 8,000 and counting every quarter. So it's really important for you to put in which specific ID it is. You can find it one of several ways. Each website, if you find it on the website, it's actually embedded into the address. And you can also see that it's on the individual CMF page right there. It gives you the ID. Then you can also, when you find that you are looking at a research study or any other report and they have cited their specific ID, then you can search for it using that single CMF ID. So it's really useful in being able to follow along what your peers are doing. It's a really great thing. So as we say, please cite the site. It's really important that we do that. All right, and very importantly, we just updated the CMF Clearinghouse Most Wanted list. Basically, that represents an analysis of user searches made from July. This last one that we just updated is July 2019 to September 2023. and is posted online at this link on the website. Essentially, the question was posed, what are people searching for but not finding? These items represent areas where crash-based safety evaluation research is needed, grouped by themes. This list can be used by the safety research community to prioritize research needs statements, particularly those which deal with the evaluation of specific countermeasures. So these are things people are looking for but not finding. All right, so wrapping up, I just wanted to give you some follow-ups specifically on comments on older studies that did not explicitly report CMFs. I think there was a question about what do we do with the old ones. So far, we don't take them out. As we mentioned several times, we have re-rated everything using the new, more rigorous methodology. But we are specifically working, and it's ongoing, on basically providing comments where this is the case so that people can look at it and say, hey, you know, these were not explicitly mentioned in the report. Secondly, the domain change tasks and programming recodes are complete. We're working to fix some 508 compliance issues, but anticipate completion hopefully within the first half of 2024. And following today's couple of other things, when you exit the webinar today, a brief survey will load. We would really appreciate it if you could provide feedback on our performance. It really helps us to evaluate our own programs and, you know, make sure that we're always doing better for the next time. Following today's webinar, you will receive a follow-up email. It will include a link to download a printable certificate of attendance for 1 hour of professional development instruction. If there were multiple attendees at your site, please forward this link to the other folks in the room so that they can download and print their certificate with their name. Okay, so that concludes this year's webinar on the CMF Clearinghouse. Again, thank you to our presenters today for sharing their experience and practices with us, and all of you for taking the time to join us today. So with that, thank you so much. Have a great day and be safe.